Good afternoon, everyone.
Oh God.
Allie, Glamour.
Cooper.
Oops. Okay, so what I want to do today so last time we talked about finding net force if I gave you like the numbers. Remember, net force is what happens if you have more than one force and you're trying to come up with how those forces, what the total effect of all those forces is. So we're going to take that to the next level where we're also going to now talk about if there's one or more of those forces that we don't know, how do we label those and how do we calculate them? So we're going to take a little bit of notes and then we're going to do a little bit of practice. We're going to basically do all the practice together, but I will at the end ask you to take a picture of your work and just because it'll be easier. I just want to make sure that that what you're seeing is important and including in your work is the same thing that I'm expecting. So I can let you know if there's anything that needs to change. So make sure that you're following along today because I will, and that you're writing it down in your notebook or on a sheet of paper because I will be collecting it at the end. All right. So go ahead, if you have your notebook at home, go ahead and get out your notebook. If you don't have your notebook, just get out a sheet of paper. And then we are going to start there. Okay. So your notes for today, you can label them dealing with multiple forces. And so last time, if I just to show you, just to remind you what we did last time, right? So last time we were drawing these things that we called free body diagrams, and we were like filling in numbers on them. Today we're going to be talking about generally, instead of just saying that the force is so many newtons, what do we call the forces? And so there are 6 types of forces that we're going to use in here. And I'm going to write them down and define them for you real quick. So the first one is called the applied force. And you are going to want to write this down because we're going to be referring to it today and beyond. So the applied force is abbreviated F with a subscript A. So applied force, we're going to abbreviate FA. And the definition of an applied force is any generic push or pull. Welcome, Brendan. Sorry, that was probably you earlier now that I see it. I just didn't know who that username was. So 6 types of forces. The first one's applied force, which is any generic push or pull. The second one is tension, which we're going to abbreviate FT. FT, tension, is going to be like if you've got a rope or you've got a cord or something. So a tension is a force caused by a rope or a cord, etc. The next one is friction, which we're going to abbreviate FF. So friction is, so you kind of know what friction is. Like if you rub your hands together, that's friction. But the key that I want to get about friction is a force that happens between forces that opposes motion, right? So it's always going to be trying to slow you down. It's going to be always go against the direction you're moving. So a force caused by a surface that opposes motion. And if you need to stop me to ask any questions, or if I'm going too fast, please feel free to speak up or write something in the chat. All right, so we're halfway there. 3 of them. Next ones we're going to call air drag or air resistance. We're going to abbreviate that FD. And air drag is very similar to friction, except it's not due to a surface. It's due to air, right? So when something kind of plows through the air, it's actually a third law thing. When as an object plows through the air or puts a force on the air puts a force back on the object. So we're going to say it's a force due to air that opposes motion. All right, the last 2 are the easiest 2, but also the most important 2. The next one we're going to write down is weight. Weight is just another word for force of gravity. And we're going to abbreviate that FG. And I'm not really going to say much about that because you know what it is, right? Gravity pulls things down. So I'm just going to say this one's self-explanatory. And then the last one is something called the normal force. Fn. Now, here's how I like to think about normal force. If you're standing on the ground, you know that there's gravity because you're not flying, right? So there's gravity pulling you down. But why don't you keep going down? You don't keep going down because there's also a surface there. And whenever there's a surface, that's what we call a normal force. The reason we call it a normal force, normal is a mathematical term that means perpendicular. So if you have a surface and you have a force pointing perpendicular to it, that's why we call it that. But basically, all I want you to know about a normal force is a support force due to a surface. So it supports you from falling. All right. Give me 1 second here we're going to do a couple practice problems with this. Let me pull them up. Anybody still need this slide? All right, if I take this down. All right, here's what we're gonna do. So I'm gonna do my work on the PowerPoint here, right? But you'll just obviously just do it in your notebook. And like I said, it's important that you follow along here because I'm gonna collect this at the end because I want to make sure that the key points that I'm trying to get across, that you're seeing the importance the same way that I'm expecting you to see it. So let me turn off my video here. So I'm gonna do this. So in your notebook, you can just write, so this is problem number 1. And problem number 1 says this: a cat sits at rest on the top of a table. So if you imagine that, question A says, is the cat in mechanical equilibrium? Now, remember, equilibrium, that's what happens when all the forces are balanced. So go ahead, and anyone can go ahead and say this in the chat. But if you could, in the chat, tell me, do you think that this cat is in mechanical equilibrium? Oops, sorry. What do we think? Go ahead and put in the chat whether you think it is or is not. So Brendan's saying yes. And I'm going to agree that it is in mechanical equilibrium. Anyone know why it's in mechanical equilibrium? How about because it is not moving, right? If it's not moving, that's going to mean it's in mechanical equilibrium. All right, so then we're going to draw a free body diagram. So this is the new thing. So a free body diagram, right? It's going to always start with a dot. Okay. Now, in the notes we just took, we wrote down 6 types of forces, and I want to think about, of those 6 types of forces, I'm going to say there are 2 of them that are acting on the cat. So, see if you can figure out which. Like, give me a force in the chat that is probably acting on the cat. Of those 6 forces we wrote down, which one's likely acting on the cat? I will give you a hint, right? It's not flying. Why is it not flying? Which force is keeping it from flying? Yeah, weight or force of gravity. I agree, Delay. Okay, silence. So we're going to draw the force of gravity. Now, in a free body diagram, we're going to draw all the forces coming out of the dot. So I'm going to draw a force of gravity pointing down, coming out of the dot. But again, this thing is not falling, right? It's not falling because there's a surface there. So what is the force from the surface that's supporting it? What would we call that? Anybody got an idea? Take a look at the explanations. Normal force, yes, Nate. So we're also going to draw a normal force. And if this thing is really in mechanical equilibrium, which we said it was, I should draw the normal force being the same size as the force of gravity. So they should cancel out. So see what it said in B. It says draw a free body diagram. Make sure to include the net force. So in this case, if it's in mechanical equilibrium, the net force is 0. So I'm going to go ahead and write that. F net equals 0 newtons. So that's how to draw a free body diagram. Oops, sorry. That's part B. Part C says if the cat's weight, oops, that is its force of gravity is 90 newtons, what is the normal force acting on the cat? So what we're going to say here is it's telling us that, that the force of gravity here is 90 newtons. So I'm just going to label that in my diagram. And if the force of gravity is 90 newtons, but my net force is 0, how much force has to go up? What would the number be? 90. Yep, good. 90, they got to cancel each other out. So we're going to end by saying, what's the normal force? The normal force is 90 newtons. So what did we learn here, right? We learned, we think about whether or not it's in mechanical equilibrium first. Then we look at the 6 types of forces that we put in our notes. We draw which of them act on it. That's what we did in the free body diagram here. And then we plug in any information we know in the diagram, and then we would say, okay, if there's 90 newtons down, there also has to be 90 newtons up. And so that's how I solve that problem. All right. Any questions about this so far? All right, let's go on to a different one. So this one's about a car moving at a constant speed. Is a car moving at a constant speed at equilibrium? What do you think? And this time, if you so give me an answer as to yes or no and why. Is this car in mechanical equilibrium? What do we think? Remember, the last one was in mechanical equilibrium because it was at rest. Do we think this one's in mechanical equilibrium as well? Well, let me go back for a second to the first law. You guys remember the first law tells us what happens when there's no net force. It tells us what happens unless there's a net force acting on it. And there's two things that can happen without a net force. One of them is being at rest. What's the other thing that you can have no net force and do? You can either be at rest, or what's the other thing the first law talks about? An object at rest stays at rest, or constant speed, right? Good. Or it stays in motion at constant speed. So we're going to say in this case, since the car is moving at a constant speed, is it in mechanical equilibrium? Yes, it is in mechanical equilibrium because the speed is not changing. All right. So there we got that. Now we got to draw a free body diagram. So again, a free body diagram starts with a dot. There are 6 types of forces. We've got actually a number of forces acting on this. What is a force that might be acting on this? We'll start with the obvious one, right? It's a car. It's not flying. So there's probably gravity holding it on the ground. But it's also not falling. It's on the surface. It's on a road. The road is preventing it from falling, right? So we're going to have a normal force that cancels out gravity. So we'll start there. I think there are 3 more forces. What do you think we would call the force of the engine pushing the car forward? Applied force, yes, Nate. So the engine pushing it forward, that's a generic push. So we're going to draw the applied force going forward. There are 2 more. If you take your foot off the accelerator so that you don't have an applied force anymore, you'll still eventually stop. What is it that's stopping you? What is it that's fighting against your motion? Well, gravity, we've already drawn gravity. Gravity goes down, but yeah, friction. And gravity, it turns out, is related to friction. But the idea here is what's actually slowing us down is friction going backward. And there's some air resistance too that also opposes motion. Now I want you to notice how I'm going to draw this. So if I've got 2 things pointing back, I line them up end to end like this. So there's friction, there's drag, FD. And the other thing I'd like to point out to you, right, is that I've drawn it, since we said it's mechanical equilibrium, the net force should be 0. So the length of these 2 arrows put together should be about the same as the length of this arrow. And then to finish up the free body diagram, we're going to say, okay, the net force is 0. All right. So that's part B. All right, part C says the car has an applied force of 700 newtons. Sorry, applied force of 700 newtons, so I'm gonna do that. Right, that my applied force here is 700. And it has a, does it say friction? Yeah, friction force of 300 newtons. So I know that this one is 300. So the question is, what is drag? So again, we said, yep, 400, Brendan. Correct, because I need my forces to cancel out, right? So if there's 700 going to the right, there has to be 700 going to the left. There's already 300 here. So I'm left with, so 700 minus 300 minus the drag should equal 0. And so the drag is going to come out to be 400 newtons. All right, any questions there? Okay, we're going to do one more together, and then I'm going to have you try 2 on your own. So here's the last one we're going to do together. It's the same car, but this car, instead of it being at a constant speed, we're going to say that this car is now accelerating forward. So if a car is accelerating forward, is it in mechanical equilibrium? Remember, the 2 ways to be in mechanical equilibrium are to go at a constant speed or be at rest. So Brendan is correct. This is not in mechanical equilibrium because the speed is changing. It's accelerating. It's accelerating. That's the answer to A. B says draw the free body diagram. Make sure to include the net force. It's the same car. So the free body diagram is going to look very similar with one difference. In order to accelerate, what has to be different than the previous one? How do I make it not in mechanical equilibrium anymore? I still have my friction. I still have my drag, same as before. But the difference is, yes, Nate, the difference is the applied force has to be bigger because I've got to accelerate, right? Now, whenever you've got a situation where you're not in mechanical equilibrium, I want us to draw the net force. The way I draw the net force is as a double arrow that is unattached to the diagram, right? So now we're saying the front force is bigger than the 2 backward forces. So I'm going to draw a double arrow going forward. I'm going to call this the net force. That's my free body diagram. All right. So we'll do part C here. The frictional force and air resistance are the same as the previous problem, right? I can't remember which is which. How much was friction in the last problem? Anyone have it in front of them? Well, you should all have it in front of you. I don't remember what it was. Someone tell me what friction was. Yeah, okay, good, thank you. So the friction force in the last problem was 300. The drag was 400, I think. And I want to know the applied force. No, I don't. Tell me the applied force. It says the applied force is 900. So I want to know the net force. So if I've got 900 going up going forward, and then I got 300 and 400 going back. What's the net force? Which direction is winning? Forward is winning by how much? Yeah, 200 newtons, right? I should have 900 minus 300 minus 400. So the net force should be 200 newtons forward. All right. Questions? I'm going to ask you to try the next two. All right. So here you're lifting a bucket with a rope. The force on the rope is 45 newtons and the bucket has a weight that is force of gravity of 23 newtons. So you go ahead and draw the free body diagram. So I'm going to give you a minute to do that on your own. All right. There are two forces acting on this. What are the two forces? Tension and gravity, right? We got a rope. A force caused by a rope we call tension. And we have gravity. Now the key though is that if I'm lifting this bucket up, right, tension should beat out gravity. And then to make a complete free body diagram, I will include the net force. And this is saying that my tension is 45 newtons. It's saying that my gravity is 23 newtons. So you should then be able to find the net force. Force should be the upward force minus the downward force. So 22, I think. All right. Any questions? One more problem. So this one's just a tad more difficult, but it's not too bad. I'll start out with you. Newton's second law gives us the equation F net equals ma. So we've seen this. Oops, sorry. Just a minute. All right, now I've lost you. Just a second. Screen sharing stopped. Okay. All right, there we go. All right, so you've seen this equation F net equals ma before. So this first part, we're just going to use that equation, right? F net equals ma, and solve for the net force. Which I think is 144 newtons. All right, see if you can draw the free body diagram. It says ignore air resistance. So see if you can draw the free body diagram. All right. So I would like everyone to just put one force that you know exists on here. So everyone needs to have an entry in the chat. I want everyone to share at least one force that they know needs to be drawn on this, but only one. So if everyone shares one in the chat, then we'll have a good list to talk about. So everyone pick one of the forces that you think acts on this and type it in the chat. All right, Cooper, I agree. Yes, I agree, Nate. Yes, Blake. Applied, FG. So we definitely have applied and FG are on there, so I'll start there. Anything else besides applied and FG? Yeah, so if this thing now, so we got applied and FG, but now if we look at this thing's going to go forward and down, but that's not what the bicycle isn't going down. What is preventing the bicycle from going down? Normal, good. Okay, good. So Andrew, one thing I want to point out, so the net force, I'm glad you brought that up. The net force is going to be always something separate than these. So we're going to call it in for, which is F in. When I say F in, I'm referring to the normal force. That's what happens if you're on a surface. The net force is going to be what the overall effect is. All right, so good. We got gravity normal applied. Oh no, don't go away again. All right, gravity normal applied. I got one more force that I have on it. Got what the last force is. Yeah, that's it. And this says that the bicycle is experiencing 52 newtons of friction. And we just found over here, right? We just found that the net force was 144. So I can draw that my net force. So here to what Andrew was saying a second ago, right? So I'm going to draw my net force as something separate. So I draw my net force as a double arrow. And in this case, we found that the net force was 144. So what do we need applied to be in order for the net force to be 144? Try and figure out what you think the applied force should be for part C. Okay, so Trey, that would be right if I did this, right? If it was 144 here and 52 there, then the net force would be 88. So what we got to do, we got to be careful about when we add and when we subtract. Yeah, so Nate, so it actually is 196, and I want to talk about how it's different, right? If I said it was 88, right, which is a reasonable thing to think, you can go back and look and see, does 88 minus 52 give us the net force? And it doesn't. what does is 196, right? So the other way to think about this, if you're not sure, is to set it up as a math problem. We could say that whatever the applied force is minus 52 has to be 144. And so if I add 52 to both sides, it has to be, the applied force is 196. Yeah. Yeah, no, that makes sense, Trey. Because there are other times, like for example, in the last problem, what you did would have made sense, because in the last problem, I gave you these two forces and asked you for the net force. In this problem, since I gave you the net force, you have to do something different. All right. Any questions? We're going to get more practice with this, and I'm going to, I really wanted to walk you through this today. Next time, there'll be more chance for you to kind of do it on your own. But let me just show you one more thing, and then we'll be done. Like I said, I would like to see how you're showing your work, because there may be some things that I want you to fix. So I'm just grading this for completion, but I do want to be able to check it. If you would go to today's Schoology page and find the day 36 assignment. So take a picture, ideally use Cam Scanner or Genius Scan if you have it, but if not, just go ahead and take a picture and upload that here. And then when you upload that here, then you're done for the day. All right. So you can go ahead and do that, and then you are free as soon as that's up. And have a good weekend. I will talk to you again on Tuesday.